at different points in space. So I should be able to do it for a point charge. I should be able to do it for a spherically symmetric distribution of charge. I should be able to do it for a wire. Usually we're talking about long wire, so that we're not talking about, because for a short wire there is some variation in the electric field due to the fact that the wire ends, right? But if we're just talking about some long wire, I'm just interested in the section that's near the middle of the long wire, then the electric fields due to the ends, way down the ends of the wire, don't change that much, or they don't have a huge effect. They basically cancel out. You still have essentially just radial electric field away from the wire. You also need a cylinder. And then the last thing that might be useful is an infinite sheet, which is really just saying, we have some large plates, right, and they're very large compared to the area that we're interested in measuring, the area where we're interested in measuring the electric field, right? So I would use different geometry for different situations of different distributions of charge. For a point charge or a spherically symmetric distribution of charge, I would use a sphere, right? So for these, I would use a sphere with surface area equal to 4 pi r squared and volume equal to 4/3 pi r cubed, right? For a long wire or a cylinder, right, I would use a cylinder where the area, right, I'm not interested in the ends of the cylinder, I'm only interested in the curved part of the cylinder, right? I'm oriented so that my cylinder is along the cylinder or the wire that I'm talking about, right? So the axis of the cylinder is along this, the long axis of the cylinder is along the axis of the wire, or along, or it just matches up with the symmetry of the cylinder we're talking about. And so I'm only interested in the area of the curved part of the cylinder, which is just 2 pi r times L, right? We have R and L, right? And the volume is just pi r squared L. Right? And the reason I'm putting the volume here is right because if I have some charge density in each of these cases, some charge density rho, then that would give me the enclosed charge by just multiplying the charge density times whatever volume I have. And then for an infinite sheet, I can use either rectangular box or a cylinder. And I come up with the same answer either way. And I'm just going to assume that you can figure out the surface area of a rectangular box. Yes? Okay. Right. So remember, when we're talking about electric flux here on the left, we're always only interested in electric flux that is perpendicular through some surface, right? We're trying to make it so that if it's perpendicular through the surface, that means that E and dA are parallel, right? So in other words, the electric field is traveling through the surface. If it's perpendicular to the surface at all points, that means it's parallel to my dA vector at all points. All right, we're not interested in portions of our Gaussian surface. Our Gaussian surface always has to be closed, right? We can't just leave one end open, right? So it's always got to be closed so that the electric flux is, so that it's enclosing some charge. But we're only interested in the parts of the Gaussian surface where the electric field is perpendicular to the surface. So for instance, that's why I'm not interested in the ends of the cylinder when I'm talking about a wire or a long cylinder, because there's no electric field going through those ends. No electric field is perpendicular to those ends. All the electric field is parallel to those ends, and therefore, when it's parallel, there's no electric flux. Because the electric flux, again, is E dot A. And so if E is parallel to A, E dot A is E times A times the sine of, times the cosine of the angle. Or excuse me, if E is parallel to that surface area, then E and A are perpendicular. Excuse me. And so it's E a cosine theta, and in this case theta would be 90 degrees, cosine theta is 0. Right? So there's no electric flux through the ends of the cylinder, for instance. Just as when I have an infinite sheet, there's no electric flux through, so say for instance, this is my infinite sheet of charge up here with the screen, there's no electric flux through any surface in this direction, right? All the electric field is out of the screen or into the screen, that's it. So we only have to worry about, we have to just arrange our Gaussian surfaces with theirs. The flat part of it, like this, is the only part that we're interested in. Now we still have to have, in the case of an infinite sheet, a surface that goes through our sheet and has two ends, one end on the back and one end on the front. We have to consider those two ends, but we don't have to consider any of the sides that run through the sheet perpendicular to it, because there would be no electric flux through those sides. Okay. So I guarantee there will be a Gauss's law problem in the final. Okay. Electric potential. Not to be confused with, electric potential energy. Not to be confused with electric potential. I'll put them right next to each other. So as not to confuse them. So one of these has units of joules, and the other one has units of joules. And the other one has units of volts. All right, so that's the first part of this. So not get them confused. Electric potential energy is usually described as U, the way that we usually describe potential energy. We have 1 over 4 pi epsilon 0, where epsilon zeros are electric permittivity constant, free space, Q1, Q2 over R. That's true for point charges. So if I have 2 point charges, and then the electric potential, V, is due to only 1 point charge. 4 pi epsilon 0 Q over R. If I have many charges, now instead of just point charges, then I have to add up the total electric potential energy, and that would be Q naught over 4 pi epsilon 0 times the summation of Qi over Ri from I to whatever number of charges I have. Right? So I have a whole number of terms here. Right? I have to add up all the different pairs in order to get the total electric potential energy. So if I have 4 charges, how many terms do I have? 2 terms.